The branch circuit described is compliant with the National Electrical Code. Let's break down each component to understand why. Firstly, regarding the conductors, the number 2 gauge wire is rated to carry 130 amps, which exceeds the 100 amp breaker's rating. The number 10 gauge wire is rated to carry 30 amps, matching the 30 amp fuses in the disconnects. Secondly, concerning breakers and fuses, the 100 amp breaker safeguards the number 2 gauge wire against overcurrent. The 30 amp fuses protect the number 10 gauge wire and any equipment connected to each disconnect. Thirdly, let's look at the distribution block. The distribution block is rated for a minimum of 100 amps and provides a practical way to connect the number 2 gauge wire to the 3 number 10 gauge wires. Finally, the 10-foot length of number 10 gauge wire falls within the permissible limits for a branch circuit. In summary, the branch circuit is protected against overcurrent by the breaker and fuses. The conductors are appropriately sized for the load and the breaker or fuse protection. The distribution block is rated for the current being used, and the length of the number 10 gauge wire is within code. Therefore, the branch circuit is in compliance with the NEC and is considered safe for use. When designing or inspecting electrical circuits, it's crucial to verify conductor ampacity. Number 2 gauge copper wire, as mentioned, typically has an ampacity of 130 amps under certain conditions, such as being rated for 75 degrees Celsius. The ampacity must be sufficient for the overcurrent protection device, which in this case is the 100 amp breaker. If the wire's ampacity were lower than the breaker rating, the wire could overheat and potentially cause a fire hazard. The number 10 gauge copper wire's ampacity is typically 30 amps when rated for 75 degrees Celsius. This matches the 30 amp fuses used in the disconnects, ensuring that the fuses will trip before the wire is overloaded. Overcurrent protection is a fundamental safety principle in electrical systems. The 100 amp breaker protects the entire branch circuit from excessive current draw. If the current exceeds 100 amps, the breaker will trip, interrupting the circuit and preventing damage to the wiring and connected equipment. Each of the 30 amp fuses in the disconnects provides localized overcurrent protection for the individual circuits connected to those disconnects. If any of these circuits experiences an overcurrent condition, the corresponding fuse will blow, isolating the fault and preventing it from affecting the rest of the system. Distribution blocks are essential components in electrical panels and enclosures. They provide a safe and organized way to distribute power from a larger conductor to multiple smaller conductors. The distribution block use must be rated for at least the same current as the main breaker, which is 100 amps in this case. This ensures that the distribution block can handle the full load of the circuit without overheating or failing. The length of the number 10 gauge wire is also a factor to consider. While a 10-foot length is generally acceptable for a branch circuit, longer lengths can lead to voltage drop. Voltage drop occurs when the voltage at the end of the circuit is lower than the voltage at the source due to the resistance of the wire. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for calculating voltage drop and recommends limiting it to a certain percentage of the source voltage. In most cases, a 10-foot length of number 10 gauge wire will not cause significant voltage drop, but it's always a good practice to verify the voltage drop calculation, especially for longer circuits or circuits with high current loads. The National Electrical Code, NEC, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including conductor sizing, overcurrent protection, grounding, wiring methods, and equipment installation. Compliance with the NEC is essential for ensuring the safety of electrical systems and preventing electrical hazards. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. This means that electrical installations must comply with the NEC in order to be approved by inspectors and to be considered safe. The NEC contains numerous tables and calculations that are used to determine the appropriate size and type of conductors, overcurrent protection devices, and other electrical components. These tables and calculations are based on scientific principles and engineering practices. They take into account factors such as the ampacity of conductors, the interrupting capacity of overcurrent protection devices, and the voltage drop in circuits. One important concept in the NEC is the concept of ampacity. Ampacity is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on its size, material, insulation type, and the ambient temperature. The NEC provides tables that list the ampacities of various types of conductors under different conditions. Another important concept in the NEC is the concept of overcurrent protection. Overcurrent protection is the use of devices such as circuit breakers and fuses to protect electrical circuits from excessive current. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level, interrupting the circuit and preventing damage to the wiring and equipment. The NEC specifies the type and size of overcurrent protection devices that must be used in different types of circuits. Grounding is another essential safety practice in electrical systems. Grounding is the connection of electrical equipment and circuits to the earth. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip overcurrent protection devices and prevent electrical shock hazards. The NEC specifies the requirements for grounding electrical systems, including the size and type of grounding conductors and the methods for connecting equipment to ground. Wiring methods refer to the ways in which electrical conductors are installed and supported. The NEC specifies the types of wiring methods that are permitted in different locations and applications. Common wiring methods include conduit, cable, and wireways. The NEC also specifies the requirements for the installation of electrical equipment, such as outlets, switches, and lighting fixtures. This includes requirements for the spacing of outlets, the height of switches, and the types of fixtures that are permitted in different locations. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include standards published by organizations such as the Institute of Electrical and Electronics Engineers, IEE, and the National Electrical Manufacturers Association, NEMA. They may also include local codes and regulations that are specific to a particular jurisdiction. It is important to be familiar with all of the applicable standards and regulations when designing and installing electrical systems. Electrical work can be dangerous, and it is important to take precautions to protect yourself from electrical hazards. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing circuits before working on them. If you are not qualified to perform electrical work, it is best to hire a licensed electrician. Licensed electricians have the training and experience necessary to perform electrical work safely and in compliance with the NEC and other applicable standards. Here are some additional details about the specific components mentioned in the question. The number 2 gauge wire is likely copper, although aluminum is also a possibility. Copper has a higher ampacity than aluminum for the same gauge size. The insulation type of the wire also affects its ampacity. Common insulation types include THHN, THWN, and XHHW. Each insulation type has a different temperature rating, which affects the ampacity of the wire. The 100 amp breaker is likely a thermal magnetic breaker. Thermal magnetic breakers use a thermal element to trip on overloads and a magnetic element to trip on short circuits. The breaker must have an interrupting capacity that is sufficient for the available fault current at the location where it is installed. The distribution block is typically made of metal or plastic and has multiple terminals for connecting wires. The distribution block must be rated for the voltage and current of the circuit. The number 10 gauge wire is also likely copper, although aluminum is a possibility. The insulation type of the wire also affects its ampacity. The 30 amp fuses are typically cartridge fuses or plug fuses. Cartridge fuses are used to disconnect switches and other equipment. Plug fuses are used in fuse boxes. The fuses must have a voltage rating that is equal to or greater than the voltage of the circuit. The disconnects are used to isolate the individual circuits connected to them. The disconnects must be rated for the voltage and current of the circuit. The length of the number 10 gauge wire is measured from the distribution block to the disconnect. The NEC specifies the maximum allowable voltage drop for branch circuits. The voltage drop depends on the length of the wire, the current flowing through the wire, and the resistance of the wire. If the voltage drop exceeds the maximum allowable limit, the wire size must be increased. In this specific scenario, the 100 amp breaker is protecting the number 2 gauge wire. The number 2 gauge wire is feeding the distribution block. The distribution block is then distributing the power to 3 separate circuits, each protected by a 30 amp fuse and connected to a disconnect. The number 10 gauge wire is connecting the distribution block to the disconnects. The 30 amp fuses are protecting the number 10 gauge wire and the equipment connected to the disconnects. Since the number 2 gauge wire is protected by a 100 amp breaker and the number 10 gauge wire is protected by 30 amp fuses, the circuit is considered to be properly protected against overcurrent. The distribution block is rated for a minimum of 100 amps, which is sufficient for the load. The length of the number 10 gauge wire is 10 feet, which is within the allowable limits for a branch circuit. Therefore, the branch circuit is in compliance with the NEC and is considered safe for use. When working with electrical circuits, it is important to follow all safety precautions and to consult with a qualified electrician if you have any questions.